Welcome to this second of a whole series of webinars that are presented by the International CCU Assessment Harmonization team. Welcome back to those of you who have joined us last week already, and welcome to those of you who are new to this series. What brings us together is a joint interest in looking at how we best assess in a harmonized way carbon capture and utilization technologies from an economic and environmental point of view. Today, we have three components to the webinar, and I would like to introduce those in the context of the series that you have all seen in the registration. We are today hearing from Tim Scone from the National Energy Technology Laboratory on how to define the comparison product system representativeness based on the technology readiness level of the proposed product system, a recommended approach. It's a long and very detailed title, but you will hear why this is important. This will take us about an hour, after which we have a brief overview provided by Michael Wang from the Argonne National Laboratory on baseline scenarios and their role. Before we conclude in the third part on technoeconomic assessments and life cycle assessment case studies of CCUS using a harmonized method. This is going to be a presentation led by Yusong Lee from Argonne National Laboratory and Gregory Hackett from the National Energy Technology Laboratory. But for now, it's my pleasure to introduce to you Tim Scone from NETL, who is leading us into the first of these three exciting components. Tim.
Thank you very much. Good morning and good afternoon to everyone. Once again, my name is Tim Scone, and I have the pleasure of helping to lead, guide, or be the person that writes on a great team of colleagues around the globe, working to help define the comparison case. Our objective here with this group is really to be able to take the guidance that is in the Global CO2 Initiative and the guidance that with NETL and other international guidance and start to think about what a harmonized set of guidance would look like for what is the best and the most representative case under different levels of technology readiness. As part of this team, Michelle Kreinock from NETL, Arno Zimmerman from Net Zero Partners, Stephen McCord, Marvin Bachman, Leonard Mueller, Gary Grimm, and Hannah Minton. And we look forward to having some of them participate as panelists today in our discussion. I'll move my slides. So a little bit about the goal. I started to describe this a little bit, and it's really about taking those two guidance documents and trying to come up with a more standard and consistent framework so that each of us are on the same page and have a more consistent, uniform guidance going forward around how to evaluate carbon dioxide utilization projects. The outcome of this effort is to set up and put clear guidance that aligns the approaches and clearly explains the differences and their value. The outcome will also consider the differences between emerging technologies and commercial technology comparisons. So today's webinar is really about getting your feedback on this proposed outcome of a methodology. So we look forward to your input. So let's start with framing as why is this important for those that aren't familiar. The selection of the comparison system defines the benchmark that the carbon utilization product system will be compared against to evaluate the technical, economic, and environmental performance. The state of technology readiness or maturity defines the time to commercialization. In general, the comparison point should be aligned to that state of maturity. So early technologies should be compared to the best-in-class technology in the market today, so that by the point that they come into the market after years of development, that the goal is that they will still have an environmental improvement, that the investments that you are making, that we're making, and others are making in these technologies at a very early development stage, by the time they hit the market, we want to ensure that they are going to have an environmental improvement. While I understand this will be continually checked throughout the development process, as it should, we do want to set this target as the highest possible, as we know others in the market will be improving their environmental performance, as well as with those that exist in the market, as well as competing technologies. Now, flipping that coin for a moment, if we look at mature technologies, We'd like to compare those against the long-run marginal cost technology to assess the indirect market consequences. When my technology is commercial and it's entering into the market, what will I displace or what will it remove from the market? And that's usually based on the long-run marginal cost. Now, if your technology is already in the market and already well established, then there's a question to be aware of from a regulatory or policy incentives may actually compare to a different comparison system, such as the industry average, to ensure environmental improvement while maximizing the regulatory or policy outcomes. So that's something to be aware of when we're evaluating these. The methodologies and the approaches that we were putting together is the best practice to evaluate whether or not the investments in these technologies and what their value would be from an environmental and economic perspective. But when we look at regulatory and policy incentives, that framework may change. And the reason for that is to drive those outcomes. And so that is understood and expected. In summary, the point of comparison may change the economic and environmental perspective of the technology or product, and which is why this makes us so critically important. Some key definitions. So proposed product system, and I must say, I want to thank our nomenclature team who presented last week. These are the same definitions within the glossary that are also available on the Access CCUS website for those that are interested in a more detailed methodology or glossary of terms. The proposed product system is the entire life cycle boundary of the carbon utilization product or service, as defined by the functional unit of the analysis. The proposed processes then are the systems inside the proposed product system that produce that equivalent function to the system in the comparison system in relation to the comparison product system. So in this case, your proposed product system is your project, your CO2 utilization project. Your comparison is what occurs today in society that produces that same service or function. So it's the entire life cycle boundary of the model that will be compared to the proposed product system. The comparison processes, similar to the proposed, are the systems inside the comparison product system that produce equivalent functions to the systems inside the proposed product system. Keeping in mind, our goal is to have functional equivalency between our proposed and comparison systems to ensure a fair and equitable comparison. So, let's define a few more terms, and these are going to be important here in the next slide or so as we talk about the classifications of how to select the appropriate comparison system. There are four options that we're going to, or four choices, I should say, that we're going to discuss today. One is average greenhouse gas. That's the environmental profile that represents the weighted mean greenhouse gas performance for production within the country that the proposed product system will be deployed. The best-in-class technology is the best-in-class technology that is defined as the process or product with superior performance. Best-in-class can be used as a benchmark against which the process or product investigated is compared. Note that best-in-class can be defined according to environmental, economic, or technical criteria. The highest market share defines the representativeness of the comparison product system as the product or service most common in the commercial marketplace, also referred to as the industry standard practice. So if you think about a data set in your common lifecycle inventory databases that represent a background data set, another LCA kind of term, it's often representative of that industry standard practice. And so keep in mind to pay attention to the metadata to ensure you know what the scope is of any of your lifecycle inventory data that you use from a third party, and make sure which definition it aligns to appropriately. The marginal cost is related to the cost relative to one additional unit of production. That's the cost of producing one more unit of a good. It's also defined as the cost increment or incremental cost. So these are just different classification systems that one could choose for defining the comparison system to propose against. So let's take a look at the recommended guidance. The team has structured this, if you look to the left of the table, based off the technology maturity. We've defined four ranges, which are generally consistent with the TRO, Technology Readiness Level definitions, which we'll hear more about. TRLs 1 to 4 is generally considered concept or lab level. TRL 5 through 6 is more of a prototype to scale up level of technology readiness. TRL 7 to 8 is more demonstration to the first plant of commercialization. And then TRL 9 is that first, second, and third plants of commercialization moving forward as it enters into the markets. Now, some of these definitions from different groups have slightly different variations, and we have a task force that's worked on harmonizing those as well, that we look forward to hearing from in the near future. We defined two sets of guidance. We defined a set of minimum expectations for reporting and a set of recommended guidance. As stated, the minimum is what we would expect to be the lowest level. If you cannot meet this level, then a data limitation should be identified in your study and remarked as to why you cannot meet the minimum expectation. This may also raise concerns over the overall quality and potentially the ability to interpret the difference between the proposed and comparison system if you cannot meet the minimum expectation. Recommended guidance is what we recommend, or the preference of what we think is the most optimal point. Remember, I talked earlier about early technologies that have yet time to go to maturity to commercialization. So those TRL 1 through 4, TRL 5 through 6. Our recommended guidance is that it be best in class greenhouse gas performance. Once again, so that by the time it's fully matures and is ready to be commercialized into the market, other improvements outside of in their competitors or in other areas will also be improving their performance. So we want to ensure that as this matures, that it's going to drive that environmental improvement that we seek. For more mature technologies, demonstration to first plant, and those entering into the beginning of commercialization, we look at the long run marginal cost. That marginal cost, what will it displace out of the market? So now we know the technology is nearing that deployment stage, and now we can do detailed market analysis, and you can begin to understand if it goes into the market, what will it replace? And will it actually replace something that's environmentally better? So this is some of that tug and pull between and trade-offs between the economics, the cost of the product that you're producing and how it enters the market versus the environmental performance of that. It's things that we need to clearly balance. And hence the focus on the harmonization of these efforts around TEA, Technoeconomic Analysis, and life cycle analysis. A few points. So data limitations below the minimum expectation must be clearly documented as a limitation and included with the primary study results and conclusions. The technology readiness level is chosen based on the proposed technology, not the comparison technology, something to keep in mind. The guidance is should level guidance as opposed to shall for the guidance text. For those that are familiar, should is recommended, shall means that you must do something in a certain way. The industry average is defined as the regional or country average. Now keep in mind, when defining that, if for your proposed system and commercial system, you already know a specific, more sub-regional or more defined geographical area for its deployment and for commercialization, you should use the most representative geographical boundary. So in some cases, the minimum here is country level, but for some, it may be a sub-region within that is most applicable for the correct comparison. That should just be clearly documented. If the industry average does not exist for some reason, then using the highest market share, what is the most dominant production method for a particular product on the market? That is often sometimes an easier data point to find. Our goal here was to balance the level of practicality with the ability to access and complete the life cycle analysis, while at the same time ensuring that we're going to get the benefits that we seek, which is understanding the environmental and economic trade-offs. And we need to ensure that that's on a functional basis, and we've set our benchmarks in the right place to ensure that value when it gets to the commercialization. Because keep in mind, we don't reap the benefits of these technologies until they become commercially deployed and enter into society. In a moment here, I'm going to open up polling with these particular questions, and you will have the opportunity to vote through that process. And we're seeking your feedback, and we have two questions we've put together today. The first question is having a minimum expectation for reporting and recommended guidance useful? So A, yes, having flexibility between a minimum and recommended guidance will help allow projects to meet available data needs without reducing the quality due to data limitations. B, no, it's unclear what the correct choice is. Or C, doesn't matter since the guidance is should and not shall. Or D, not sure or unknown. So I'm going to go ahead and open up the polling here for the first question, and I will leave this open for 3 minutes. Very good. I'm going to go ahead and end the poll and share the results. So as folks should be able to see, there was an overwhelming result for answer A. That yes, having both the minimum expectation for reporting and the recommended guidance is useful, with about 78% response for item A. Thank you very much for everybody's response and input to this process. This helps us build confidence as we move forward in finalizing the guidance around having two sets, a minimum and a recommended set of guidance. Thank you very much. Let's go ahead and move forward to the second question. Keep in mind, we will have an open Q&A immediately after the second question. So the second question to pose today is for TRL number 9, commercial technologies or products. So this is specific to commercial technologies or products. Since the product is already part of the existing market supply curve, does the marginal cost choice still make sense? Answer A, yes. Consequential LCA generally recommends the long-run marginal cost be selected for system expansion with displacement. B, no. Since it is already part of the market supply curve, industry average would align better for common economic and environmental comparisons. C, doesn't matter since the guidance is should and not shall. Or D, not sure or unknown. So I'm going to bring the screen back up that shows the table with the question. And I'm going to go ahead and open up the second polling question. And we'll leave it open for 2 minutes this time. All right. I'm going to go ahead and close the poll. Let's go ahead and share the results. As you can see, it was a very tight race between options A and B, with a good number in the not sure or unknown category. And so we did have A, that the consequential LCA using the long run marginal cost come in at 39%, with the industry average coming in at about 36%. And so I did notice a few questions coming in. And so let's go ahead and open up to the questions here for a moment. Thank you very much for everybody that responded to the second poll. It's very helpful and insightful. For the open discussion today, we'd like to encourage you, or we'd like you to use the Q&A section. So at the bottom of your Zoom panel, you'll see a Q&A button. And good. So we've had 2 questions come in on the Q&A. First question is, would it ever be possible or recommended to compare low TRLs 1 and 4 and 5 and 6 against marginal costs? The goal of the guidance document is to help set consistency in the comparison across studies being done by different entities in different groups to help make the information more uniform for decision makers and for others that are utilizing that. Now, in the guidance documents, they each state a recommended practice. We prefer that you do it this way, for example, as your base case scenario. You always have the option then to select and run a secondary scenario and provide your explanation of why you feel that an adjustment is more appropriate for the comparison. So in short, you would generate 2 sets of results. One that would follow the guidance documents, recommended guidance, and then a second scenario saying that why you believe this set of decisions or methodologies is more appropriate with your written justifications. There will always be unique circumstances where a different set of conditions based off your study is important to your decision maker or to the question of interest. And so that is always something you'll need to take into account in conducting your study. But keep in mind, and I'll drive back to the premise of why we're harmonizing and trying to create this consistency in this guidance, is so that each entity following the guidance produces a set that's more comparable across the field to one another. So next question. For the second question, one asks, doesn't decision depend on the goal of the study? Yes, to a degree, but keep in mind that the goal here is to drive that consistency again. So when we are looking across the field and trying to understand how different CO2 utilization technologies, what their economic and environmental performance looks like, we need a way to have an equivalent basis of comparison. And the harmonized guidance is that tool to do that. And so here we are trying to, in this guidance document, knowing that the goal here is technology development. So we are trying to characterize the current state of the technology from both an economic and environmental perspective. And then we are also trying to understand that if this technology entered into the market, would it perform better or worse than the current methods of producing that same service or product in society? And so in this case, that definition of the guidance document is less consequential and more attributional in a direct comparative context. You are comparing situation A to situation B, or the proposed to the comparison. And so keeping the consequential aspects out of that is important at that stage. Now, it doesn't mean that there isn't the need for a policy evaluation to understand if this goes into market, what are the long-term indirect effects and what benefits will that have? So understanding your goal and being able to articulate that alignment is important. And I'm sure others will have more comments on that, as that tends to be a lively part of discussion. So let me go back to the Q&A here for a moment. Another question, which is the technology that's currently at TRL 9, or could this mean a technology at a lower TRL but projected performance when at a TRL 9? So when we set the guidance in the table, and I'm going to flip back to that table for a moment. There we go. And we're talking about the TRL 9 commercial status here. We are referring to the technology is already at the TRL 9 technology readiness level state of maturity. There is another task team that will be presenting that talks about how to technology learning curves and how to escalate something forward to see what it would look, an emerging technology would potentially look like as it's moving into commercial development. That is a different set of guidance, which we'll talk about as a separate scenario in the methodology. For the primary basis of comparison, we are looking at the current state of maturity of that technology. But we also understand, and why it's included in the guidance documents is, and in one of our task teams, is thinking about the methodology of how you move that forward, because that creates a different comparison point. The important thing there is to recognize that now you've made assumptions about that data. And so that's an important aspect in the interpretation of your results. But I'll leave that to the group on technology learning curves to talk about. Next question is, concerning TRL 9 technology comparisons, I agree that marginal cost comparison is more adequate. However, the comparison will be dependent on regional factors. Sorry, my screen moved. Such as tax frameworks or environmental regulations, right? This is the question that's driving towards what I talked about earlier about the difference between technology evaluation for the purposes of technology development and moving it into commercial deployment, which is what these sets of guidance are designed around. How will this compare on an economic basis, and how will the environmental performance compare when it enters into the market? We do recognize and understand, as noted earlier, that under certain regulatory or policy frameworks may have certain drivers and different sets of requirements for what the comparison system is. For example, if something already existed in the market, one policy incentive might want to drive to ensure that we are improving better than the average, so that over time, as products come into the market, we are driving that average down. The goal there is to incentivize environmental performance while not setting the bar so high that you limit the number of folks that can come in and take advantage of that regulation or policy. So it opens up the playing field, so to speak, while ensuring environmental performance criteria. So if you think about things like here in the United States, the US EPA's renewable fuel standard, you think about things like California's low carbon fuel standard, other regulatory frameworks, they're all based off that average. We're driving to ensure we're driving the average performance of the field or of that product or service down. So yes, there are situations for CO2 utilization technologies where you will need to provide, we want to follow this guidance for that purpose, and then you may need to modify it to meet for the regulatory purpose. Great question. All right. Next question was, have you considered recommending reporting both ways, marginal and average, for TRL 9? That's a great question. We discussed it within our team significantly, I shall say, and the conclusion was the goal of having harmonized guidance is to harmonize that guidance to drive that consistency for comparability within the field. And so we tried to reach a consensus point where we thought one was most preferred and best given the purpose of the guidance document. So we are open to hear more feedback, but we find that that will create, it may create confusion between different studies conducted by different entities that people will not be able to adequately compare them. They will then have to go in and make their own adjustments, which can be difficult and lead to error. And so having that consistent framework is part of the drive here, but while leaving, once again, the option for additional scenarios, and you can present those to your decision maker and say, we believe this is the appropriate decision point for the following reasons. For comparative purposes with other studies, this point is the one that compares to the harmonized international CCU harmonized guidance document. And I will say, I do have a few other team members on the call, so if you are interested in fielding some of the questions, feel free to jump in or raise your hand. The next question is, what about some advantageous aspects of a specific location? Yes. So while we define this, and we have, for example, here with the industry average defined as country, we do remark and understand that you should select your geographical boundary based off of what is most representative for your technology. So if your product, and particularly what you're being compared to, is very local to a specific region and does vary regionally within your country, then you should define your boundary as the most applicable geographical regional boundary, and you should state why, is our recommendation. So I want to be very careful in any development of a harmonized guidance document. There will always be opportunities where you will see improvements in accuracy in your comparisons. You should take those opportunities to do that. You just need to define it and explain why, keeping in mind that we still would prefer that you run the international CCU harmonization as a standard result so that that's available for greater comparison. All right, moving forward, and I think this will be the last question in this session, and then I'll turn it back over to Volker. So how does data availability, example, average data or marginal cost data, limit the implementation of the guidance, and what are the ways to address such limitations? This is a great question, and this is one of the reasons why we posed the question around marginal versus average. In our group's experience, we feel that long-run marginal cost is the more applicable or more accurate for determining a technology that's just entering the market and understanding what it will remove from the market, and therefore what is that indirect effect that could have its advantage. We do strongly recognize as a group that access to long-run marginal cost data can be very difficult for very specialized items, and can be very difficult to be able to get it not only for for your comparison system. And so we find that on a more practical basis, that the industry average data is much more commonly available in commercial and public lifecycle inventory databases, or in the academic literature often will create an industry average perspective as a baseline in that work. So in our experiences, we were trying to balance what would be what we think is the most theoretically correct and best approach against what is the more practical approach to implement today, while ensuring that both approaches drove to the end conclusion of ensuring an environmental improvement if that product was deployed into society. And so this is that exact trade-off around the long-run marginal cost versus average cost. It's the balance between what we think one can practically be able to access at a low cost versus marginal cost may require more work and a higher level of resource investment in order to define a consistent long-run marginal cost technology. So that is an excellent question from that perspective. We had one more question come in, and that is, in which TRL is suitable to include carbon taxes into the economic assessment? That is a great question, and we have our third session today, which talks about the technoeconomic analysis portion, and I'm going to leave that question for our third part for them to talk about where that integrates into that process for that. So I want to say thank you very much to everybody that participated today for both your input to the polling questions, as well as your input to the Q&A session today. So on behalf of the team, we'd like to thank you for your time and your initial feedback today. And I say initial intentionally. We want to give you the opportunity to send additional feedback or your thoughts for the team's consideration prior to us finalizing our approach. And our goal is here to finalize it at the end of this month. So by June 1st, we'd like to move forward with that process. So if you have additional thoughts along these lines, these slides will be available. Please feel free to send your feedback either directly to me or any of the team members in the comparison case representativeness team. So with that, I just wanted to say thank you very much to everyone once again who's participated. And I look forward to any additional feedback. And we really appreciated your time, your attention, and your feedback today in the great questions. Volker, I'll go ahead and turn the floor back over to you.
Tim, thank you and your team so very much for all this work and putting this together, delivering it in a very succinct and accessible way, beginning the process of soliciting community input, which I cannot emphasize enough is really important. We want this set of recommendations to work for the community. So make yourself heard by sending feedback to the address that Tim had sent. I understand that the slides will be sent along to the participants, so that gives you the email address again. So in moving on with the program today, it's now my pleasure to invite Michael Wong to tell us a bit more about baseline scenarios and what his team has encountered as they looked at defining and identifying baseline scenarios.
Okay, thank you very much. Sorry for the technical difficulty. So yeah, as Volker said, I'm going to present the baseline scenarios for the whole harmonization group. This has been our effort with 7 of us since last November. As you see here are the other team members, and all of them I imagine is on the conference or this seminar. So in case if you have some specific questions of their responsible scenarios, they may chip in to address. So the background and the scope, the background of this team is to put CCU technologies into the perspectives. So CCU technologies may be compared with other carbon mitigation technologies, such as energy efficiency technologies and renewable energy supply for deep decarbonization. The future scenario of GHG reductions directly affect the choices of CCU technologies and other carbon mitigation technologies and their economics. And the TEA and LC of CCU technologies needs to have consistent, compatible future scenarios so that CCU technologies are with appropriate content. The scope of this team is to review the decarbonization scenarios developed by different organizations such as the IEA, the IPCC, and the individual countries. So the purposes are to present the baseline projection of GHG emission growth and reduction, level of needed GHG reductions to achieve climate stabilization, general technology trend for GHG emission reductions, and set of GHG mitigation technologies may be selected so that CCU technologies can compare to. So with that, here are 6 studies with baseline scenarios is developed. So as you see, the IPCC AR5, 2C, and 1.6 scenarios is by Tim Naghorst. The US ERA Energy Information Administration baseline scenarios is by Joseph Choi. Shell Scott scenarios and the US 2050 scenarios and I did the review and synthesis. At IEA World Energy Outlook and Energy Technology Perspective by Stephen McCorn. At EU Global Energy and Climate Outlook about Heritage NAMS and Princeton Study Scenario by Lim Tao. So I'm going to present the key features of those scenarios later on. So the key aspect to summarize from those scenarios are relevancy of the scenarios to CCU initiative missions. So what role specifically will CCU technologies play in deep decarbonization? The context of the scenarios specifically will look for information on the goals of reviewed scenarios, either as carbon reductions as the goal or meeting the future energy demand, carbon reduction trend in the developed scenarios, so what CCU technologies assumed in the scenarios, and the magnitude of CCU technologies deployed, and what are the other general trends in the scenarios, such as energy mix and energy demand. So as you can see, the goal is use those baseline scenarios, give the people to do the CCU technology examination abroad context. So the first set of scenarios is the IPCC AR5 scenarios by team. So these are the scenarios to reach 2C degree goal. The new scenarios take alternative futures in CO2 concentrations as their starting point, with radioactive forces trajectory from different combinations of economics, technology, demographic, policy, and institutional features. The range of underlying social economical scenarios that are consistent is potentially very widely. The IPCC assumed the near-term deployment of CCS is likely to resume some industry facilities with demonstration in place. And as we all know on this call, there are some demonstration projects already going on in different sectors. So that's the IPCC starting point for CCS. But in the long term, IPCC assumed the market for CCS systems will shift into the electric power sector. Three main classes of capture technologies are identified: the pre-combustion, the post-combustion, and the oxide fuel capture. The deployment of CCS at a scale of 100 of gigatons CO2 is consistent with the stabilization scenarios. And lastly, the BEC is one of the few technologies identified in the IPCC scenarios that are capable of removing past CO2 emissions in the air. So it's showing its role in many of the yellow stabilization pathways is important. So many of us are familiar with the IPCC scenarios. So on the right, you see many scenarios IPCC built with a wide range of carbon implications into the future. The IEA Energy Technology Perspective Scenarios was reviewed by Stephen. So there are two major scenarios, the so-called stated policy scenario and the sustainable development scenario. E-fuels with waste CO2 and renewable electricity play a prominent role in the SDC for carbon reduction. And the BECs also play an important role in the SDC. It is unclear in these two scenarios that focuses primarily on biofuel, hydrogen, and hydrocarbon-based fuels in what is discussed as the decarbonized transport sector. There is a mentioning of alternative fuels for the transport sector. So that's where we think CCU belongs to the e-fuel, the biofuel, that whole group for transport decarbonization. The details data behind the report are available on subscription. So if some of you subscribe the REA ETP, you'll be able to access all the detailed data developed for ETP. The EU Global Energy and Climate Outlook was reviewed by Harriet. So here, EU developed 2C and 1.5C scenarios. The scenarios establish much larger non-biomass renewable energy shells in 2050. CCS options, including sequestration from coal, gas, and biomass combustion, and direct air capture. CCS technology starts in 2030 and reach to 3.6 to 4.6 gigatons CO2 per year by 2050. CCU, on the other hand, is in the e-fuel space for transport. So the scenarios has the e-fuel production of 176 to 237 metric ton of oil equivalent by 2050. So This is equivalent to 3.6 to 4.6 gigaton of CO2 sequestrated by e-fuels. The U.S. Energy Information Administration's annual energy outlook, so Joseph reviewed the 2020 AEO. So as many of us know, AEO is primarily on energy demand and production. And so AEO project trends in energy demand and production, including improvements in energy efficiency. It highlights important factors of future energy production and use. All technologies are split into different end-use sectors. And greenhouse gas reductions are not the focus for AEOs so far through 2020. But on the other hand, as we all know, the US new administration has ambitious goals. Carbon neutrality, electric sector by 2035, economy-wide carbon neutrality by 2050. But there is no details yet. And we believe CCUS will be likely to play an important role, especially for economy-wide carbon neutrality by 2050. The shale scar scenarios is reviewed by me. So the scar scenarios has a goal for global net zero greenhouse gas emissions by 2070. There are significant changes in global energy supply mix through 2100. So as you see here below in the chart, the fossil energy, that's the blue bar, is going to reduce significantly from 2020 to 2100. On the other hand, as you see, the solar energy will increase share significantly. That's the yellow bar in the middle. The other near zero or zero carbon energy supply sources such as nuclear, hydro, geothermal, biofuel, biomass, and wind will step in to play important roles to displace fossil energy use. And on the right side, I pull up the CCS contribution to global GHG reductions in the shale scar scenarios. As you see from 2020, the total global CO2 emissions would be about 35 gigatons a year. It's going to reduce to about 18 gigatons by 2050. And the goal was set up by 2070 is going to be about zero. At the end 2100, it will have a negative emissions. The red numbers here are the amount of CO2 sequestered from CCS. So zero in 2020, at about 2050, about 5 gigatons, 2070, 10 gigatons, at 2100, 11 gigatons. On the other hand, last year, Shell developed some scenarios for the US with the goal of a net zero carbon energy system for the US by 2050. And Shell developed scenarios for CCS contribution. So here are listed the numbers. 2020, the total greenhouse gas emissions in the US will be 5 gigatons with zero CCS reduction. By 2040, 1.1 gigaton of CO2 emissions with 0.65 gigatons of CCS reduction. At 2050, 1 gigaton emission and with 1 gigaton of CCS CO2 reduction. And lastly, the Princeton study scenarios is for the US. And here, I'll quickly go through the mitigation measures, including ad-use efficiency, ad-use electrification, and of course, with large amount of renewable electricity. And CCS and CCU technologies are included in the Princeton scenarios. The CCS contribution to GHG reductions in 2050 is about 0.9 to 1.7 gigaton in the US. And CCU contribution is about 0.1 to 0.7 gigatons of CO2 for e-fuel productions in 2050. So these are the 6 studies with baseline scenarios, and in most of those scenarios, CCS and CCU play important roles. So in summary, deep decarbonization scenarios assume that CCS and CCU technologies will play important roles. Some scenarios are more detailed with quantified GHG reductions by CCS and CCU. For example, the shale scale scenarios, you have your specific gigaton reductions from CCS. It will be helpful, in our opinion, to put specific CCU technologies into the broad perspective of deep decarbonization scenarios as we summarize in this effort. But while providing high-level information of CCS and CCU roles, these scenarios do not offer details on economics, energy, and GHG assumptions for detailed oriented global CCUS initiative. Whereas for TEA and LCA, it's very technology detailed. And by the nature, the scenario development usually stay at high level. So they certainly do not offer details for TEA and LCA for CCUS. So this is a quick summary of what this team has gone through to summarize the baseline scenarios. So I'll stop here to see if there is any question. Okay, it looks like Antonio has a question. What is expected role of CCU technologies used in our carbon circular economy perspective in reduce non-renewable resources, in particular fossil fuels? So as I said, some of the scenarios is target on the power sector, and of course, with power sector, you would anticipate is going to fossil fuel electric power plant. So in a way, it will help the fossil fuel power plant to mitigate the CO2 emissions. And some targets to BECCS, so that's where we could anticipate negative emissions, because for BECCS, we have CO2 from the air, and then if you have sequestration of some of the CO2s, you could have negative emissions. So, this is where the CCS will play important role. But on the other hand, if we look at some of the IPCC scenarios and even the shale scenario, it has a very high penetration of renewable energy. So let's say if in the future, if we're going to move into a significant share of renewable energy supply, and fossil energy supply is going to face down, or in some scenarios is face up, you're not going to have CO2 sources for sequestration. So that's where for negative CO2 sequestrations, the BECCS and direct air capture are the potential CO2 sources. So I hope I address your question. Okay, the next question is from Antonia Pure. What could be the role of green hydrogen in CCU technology and in the industrial decarbonization, not only for energy production, but to obtain chemicals and products for daily lives? Yeah, this is a good question. So we know for energy sector, all these scenarios as we summarize the targets on energy sector, energy supply and energy demand. But we also know the materials sectors has significant greenhouse gas emissions too. Steel production, as the current technology shows, has significant CO2 emissions because use of coke. Ammonia production, use natural gas, or in some countries use coal, has significant greenhouse gas reductions. Cement has significant greenhouse gas reductions. If we envision that we're going to have a large amount of renewable electricity, and with that to produce green hydrogen with about zero carbon in hydrogen, we could use hydrogen for steel production, for ammonia production. So we could have zero carbon materials besides zero carbon energy supply. So green hydrogen will play an important role to decarbonize the materials for the economy. Let me see, I think these are the two questions for my presentation. Let me see the question above. Do you expect that capture will include more carbon utilization in concrete remove the future, especially in the LC and the TA? Yes, I capture addressed in the green hydrogen question. The materials area pose the challenge. The energy sector, as we all now see, lots of studies, but the materials areas do not have enough in-depth studies for decarbonization. This is the area now start to get some attention. Yes, and I do see with detailed analysis in those material sectors, as I mentioned earlier, steel, cement, ammonia, or even aluminum. So those are the areas pose opportunities, and in some cases challenges for deep decarbonization for the whole economy global-wise. And I do not know if this question was for me or was for a team. The trade-offs in cost and emission reductions. So let me try to address this question. This is exactly what this whole harmonization team is trying to address, to put both TA and LC together for CCU technologies. So the stakeholders and societies can look at both cost and benefit for specific technologies. I think these are the questions related to my presentation. Volker, let me know if there are any additional questions.
Michael, I think you have covered the ones that I also see. No further comments. I think, as with all the presentations that you heard here today, have heard last week, and going forth, we value feedback, we value additional inputs beyond the actual duration of the events. So feel free to get in touch. We certainly have the interest in hearing from the community. So Michael and your team, thank you so much for compiling this, providing perspective on the variety of scenarios and their role. So with that, I would like to move on and invite Yusong Lee and Gregory Hackett to share with us their team's work on techno-economic assessment, life cycle assessment case studies using a harmonized method.
Okay, thank you very much for the introduction, Volker. And my name is Yusong Lee from Oregon National Laboratory. And what I'm going to talk about today is about the TEA, Technoeconomic Analysis and Life Cycle Analysis case studies of CCUS using a harmonized method. So today I'm on behalf of the team members and I'm with the Greg Hackett from the National Energy Technology Laboratory. So we are going to talk about the LCA perspective and the TEA perspective for the case studies that we are going to evaluate. And I'd like to thank for the team members. We have Michelle from NETL and Edward and Alex from the University of Sheffield in UK. So let me get started. So the objective of this team is to perform the techno-economic analysis and life cycle analysis for the selected carbon capture, utilization, and storage technologies using the harmonized method. I think that's the most important part. So as you may have seen on the right-hand side, you see the multiple institutions, the international CCUS harmonization team. So what we have done so far and what we are going to do from these activities is to pave the road to actually perform the TEA and LCA, not just to generate the method. The methods needs to be used for the actual TEA and LCA. So what we are going to do, we are going to use those already documented, the methods and the activities that we are working on. We'd like to use the harmonized method to actually perform the TEA and LCA. And to give you the context of this team, so we are called the test case comparison team. Let me put the pointer here. So we are a test case comparison team, and I'm on behalf of this test case comparison team. And as you may see, there are many entities here, many institutions and many team members in the different teams. And each individual team for the international CCUS harmonization team work independently for the activities that was given to each team. For example, you already see from the last webinar, you already seen the nomenclature team and the website content and design team presented last time. So we have the total of 8 teams, and we have the 2 new teams here, the TEA and LCA integration team and test case comparison team. The reason that the reason that the 2 teams have just kicked off is because we wanted to leverage the results from the other teams and the feedback from this webinar. So mainly, in order for us to perform the TEA and LCA, we need to have all the detailed information from the previous teams that actually started from the end of last year. So every team here you see, and you may see from the webinar series, we will get the results of these teams, like the nomenclature, and the team just presented about the comparisons, the systems, and Michael talked about the baselines. And maybe tomorrow we are going to hear from other teams about the technology learning curve and others. So what we are going to do, we leverage the results of the other teams, and we are going to evaluate those the cases. And note that this team has just started, so we are at the initial stage. So your feedback will be really appreciated to set the plans for this team and to evaluate the pathways along we are moving forward. So what we expect from these activities, so from the TA, from the LCA perspective, we are going to perform the LCA of the selected CCUS cases, as I just mentioned, which is mainly about the environmental impacts, like the greenhouse gas emissions or the accumulated energy demand for these proposed technologies. For the TA part, we are going to evaluate the economic implications of the CCUS, and the metrics mainly include the cost by type, like the capital cost and operating costs, like labor and overhead. So our goal is to generate the TA and LCA results. But at the end, so we may not just perform the TA and LCA. We wanted to give the feedback to the other teams, because the teams actually need the feedback from the activities from the TA and LCA. So what we are going to do, after we completing this activity, we are going to provide the feedback for other teams so that each team could refine their method and refine their documentation to make this in the final report from the Global CO2 Initiative. So let me talk about the cases that we are going to evaluate from now on. So the first case is called the mineralization, or which is also called the carbonation. So you may know that the global cement production is huge. So it's estimated at 4.1 gigaton, and it's stabilized since 2014 based on the International Energy Agency. So by 2019, we have almost the 4.1 gigaton per year level of the cement production. But we expect the cement production would grow by 2030 based on the IE report. And currently, the cement industry is responsible of 8% of the global CO2 emissions, meaning if we can utilize the CO2 from the cement production facilities, then we can actually benefit reducing the greenhouse gas emissions. So the concept is take the CO2 and make additional cement from the cement industry. So that's the one case that we are considering. But other than the CO2 from the cement production facility, we are able to capture CO2 from various CO2 sources. For example, ethanol and ammonia generate high purity CO2, and other the steel iron industry generate the CO2 as well. And if we expand the system boundary, expand the feedstocks available for the mineralization, we can even consider the power plants or even DAC, the direct air capture CO2, for further production of the products like the cement here. So this is the one specific case that we are currently considering to evaluate. So the TA and LCA for this mineralization technology. And the second case that we are going to evaluate is a CO2 to jet. So the global aviation sector is expected to grow in the future. Maybe we expect that very small part of the global aviation sector could be electrified, but the majority, the aviation sector will need the liquid fuels, high energy dense fuel for the aviation sector. So the global aviation sector tried to use so-called sustainable aviation fuels, which is called SAF, to decarbonize the sector. But so far, the SAF mainly includes the biofuels, because the biofuel can displace the petroleum fuel to reduce the greenhouse gas emissions. But now they think about using CO2 as a carbon source for the SAF production, and which would give us the low carbon fuels for the global aviation sector. So again, we can use the various CO2 sources like ethanol and ammonia, steel and iron, or again, the power plants or DAC. So once the CO2 is captured, we can utilize the CO2 using the electrochemical reduction, generating syngas, mainly carbon monoxide. So once we have the carbon monoxide, we can use the hydrogen from the renewable electricity, the electrolysis, the hydrogen from the water, And using the carbon monoxide and hydrogen from these two sources, we can synthesize jet fuel using the Fischer-Tropsch synthesis. So the second case is generating energy product from the captured CO2. So we are going to develop two major cases, and maybe we are welcome to ask you, we are welcome to have your feedback for the additional thoughts on the cases. But when we analyze these cases, we are going to rely on the methods documented in the TA and LCA guidelines for CO2 utilization by GCI. That's, as I just mentioned in the beginning, we'd like to use the harmonized method, and this specific this report documents all the details about how we can perform the TA and LCA. And also, as Tim this morning mentioned about the guidance from the current ongoing activities, like how we are going to set the comparison system, that's those kind of recommended guidance from other teams will be able to help us to set the system boundary and how we are going to select the data sets, because the boundary and the data sets will be the key factor determining how we can perform the T and LCA. I'm sorry. And during the last webinar, we saw that we have the new web page, and the web page includes all the detailed information about the CO2 utilization, the T and LCA. And if you check the website here, then you will see there are templates and the tutorial videos for those templates for both T and LCA. So what we are going to do is we are going to mainly rely on the templates developed by GCI. So we have the LCA template and TA template, which is the Excel-based template. So we are going to use those templates to see whether we can analyze these two cases using these templates. Also, for we need to communicate with the other teams, especially technology learning curve team, to have the consistent conditions and to receive the relevant data sets. So the tools are tools, so we can use the tools, but in order for us to use the equivalent data sets, we need to collect the data sets from the multiple sources. And luckily, the websites includes the data of all the detailed the potential data sources. So we are going to leverage what we already have documented in those websites. So to collect the data sets from other sources, as well as one from the technology learning curve team, which will present the progress tomorrow, I believe. So I'm going to talk about the plans for the LCA, and Greg will follow up with the TA part. So here, I just want to emphasize that this is not the full system boundary. I just wanted to give you very brief system boundary. Actually, in order for us to include the system boundaries, the entire system boundary, we need to have the comparison system and the proposed system. But here, I just want to give you the sense how we are going to compare the different systems. The system boundary, as in the document, the GCI document, we are going to develop the cradle to gate results, because the downstream will be the same for both the proposed products and the counterparts, which is in the comparison system, which is the counterparts with the same downstream. So the functional units, if we consider the proposed system and the comparison system, the function unit will be the entire system generating multifunction. For example, if we take the CO2 to jet case as an example, then the jet fuel will be the product. But when we have the CO2, there will be a main product in the comparison system. That CO2 have its own main product. So that in that level, system level, we can compare the results. Also, we may have the product-specific results if we use I'm going to talk about how we are going to handle the multifunctionality. But if we want to generate the kilogram or megajoule of product results, product specific results, we can compare the results with its counterparts. So I just mentioned about the handling of the multifunctionality of the CO2 sources. So mainly we are going to use a system expansion as recommended by the document. So as Kim mentioned this morning, we have the comparison system. So the CCU has mainly two products, the CO2, like the main product from the CO2 source and the CO2 derived product. So we are going to expand the system to include all the comparable, like the main product and the CO2 derived products to have the same functionality from the system. And then we are going to compare two consistent functional unit, the two systems with a consistent functional units with the main product of the CO2 and the additional functional units. And we also want to consider the substitution method in the document. The substitution method, there's no additional functions in the functional units. It's mainly subtract the avoided emission credit for the counterparts. So that's another handling method that we are going to consider. The LCA data sets are also important part, and we may need a process level inventory. So we are going to collect the inventory at each process, but the important factor is about the harmonization among the team and the debate among the team. So we are going to communicate with the TL, the technology learning curve team, to have the consistent data sets, and also because we want to harmonize the LCA and TA, so both TA and LCA will use the same harmonized data sets. One of the important factors that we may potentially discuss is about the TLL level and the available data sets or the quality of the data sets. So we'd like to get your feedback about the quality and the availability of the data sets depending on the TLL level. And all the upstream or downstream calculation, we can rely on the existing LCA tools. So once we finish this LCA part, we are going to have the greenhouse gas emission results, and we can estimate like where would be the hotspots for the LCA results. And we can also perform the sensitivity analysis. And after that, we can provide the descriptions of the LCA procedures using this harmonized method. And eventually, we want to provide the feedback for other teams so that they can refine their reports. So let me stop here, and I'll give this to Greg for him to follow up.
All right, great. Thank you, Yusung. This is Greg Hackett from the National Energy Technology Laboratory, and I represent and I lead our Technoeconomic Analysis group with respect to carbon utilization technologies, as well as high temperature solid state electrochemical devices. Yusung is going to advance the slides for me, so if you go to the next one, please. So as Yusung mentioned, this group has just stood up, so this is going to be a high level presentation on the process that we're going to go through, similar to what Yusung presented for the LCA with respect to our techno-economic assessment methodology. Most of you are probably familiar with these types of analyses, so I'm not going to spend too much time on why techno-economic assessment is important, as opposed to jumping right in to talk about the strategy and what we're going to do. Being from NETL, I'm familiar with the NETL process for conducting techno-economic assessment. I have reviewed the Global CO2 Initiative guidance documents as well, and they're pretty well harmonized. So one of the first steps of this process will be to iron out any details as we move forward. As Tim Scone mentioned in his, the consistency is going to be very important in conducting these analyses, especially if we're setting up test case and example analyses to include in guidance in the future. So I'll start out by just a broad data point here that techno-economic analysis provides a methodology for systematically comparing technology states to a fixed reference case, allowing for quantification of the benefits of the technology of interest. And so defining the system boundary of the technology of interest is a critical consideration for understanding the applicability and the limitations of the analysis. And you'll see as I progress through the slides, This is one of the important first steps of doing the analysis. So one of the slight differences between the Global CO2 Initiative recommendation setting the TEA system boundary at cradle to grave to match the LCA, NETL typically assesses the specific technology from a gate-to-gate perspective, where we really dive down into the technology itself. So this is of relative importance. It can change depending on the technology that you're looking at. It might be important to look at how the carbon is captured, what the source is, and the purity. So it might be important to expand the front end from beyond the gate to the cradle. But typically we focus on the technology itself. So that'll be something that we iron out right up front. If you go to the next slide, please. So the methodology that, once again, this is developed from a combination of the Global CO2 Initiative guidance and the NETL guidance. But the methodology applied involves the following four-step process. Step one is the development of a technology analysis plan. Step two, create a performance model. Step three is cost estimation. And step four is reporting. Specifically for carbon utilization processes, additional considerations are required. For example, and I mentioned this a little bit briefly previously, the carbon capture process. Is the analysis carbon capture technology dependent or carbon capture technology agnostic? And I'll talk a little bit about that when we get to the metrics discussion. And the scenario analysis, are learning curves or sensitivity analyses more appropriate based on the technology readiness level? So you can see that there's a lot of coordination with the other teams that have been working on these two cases before. Next slide, please. So the next 4 slides are going to dig into a little bit more detail on each of the steps along the TEA methodology process. So a technology analysis plan is the roadmap for executing a TEA. It discusses the approach and the methodology required to conduct the analysis. And it should be discussed with the end users prior to initiating the analysis. And it is updated as the TEA is performed. As you analyze the data that you have, there might need to be changes in what metrics are important or data gaps that need to be addressed, so on and so forth. So it is a living document, plan document that needs to be updated as you progress. And it should address the following. What is the objective of the analysis? And that's first and foremost, what are you trying to show with your analysis about the technology specifically? There's a lot of different things you can look at, which I'll talk about here in a little bit. What is your reference case or scenario? What are the novel cases, scenarios that you're going to evaluate? And in this case, that's pretty well defined, as Yusung mentioned earlier in the presentation. And if there's a novel design, what is the design basis? Do you have enough information to evaluate performance, cost, what any types of sensitivities, and what timeline are you looking at? What's the execution timeline? Next slide, please. So one of the most important things to understand the technology and how it's going to perform is the development of a performance model. And this can be done with available software. NETL typically uses Aspen Plus, ChemCAD, or ThermoFlow. And then you have to consider, what are you looking to hold constant? Is it the chemical product rate? Is it the amount of energy that you're inputting into the utilization system? Or is it the amount of CO2 that you want to use? So that's a critical consideration on what you're holding constant for the analysis. You need to understand how balance of plant equipment will be affected. If you're using readily available balance of plant equipment, maybe operating off spec could affect the performance and cost appropriately. So you need to understand that. Process flow diagram to help map out exactly what the system will look like. And then you need specifications such as the input purity specifications. So for example, if you're inputting a pure stream of CO2 or you're trying to remove CO2 from a fossil fuel-based flue gas, those are very different scenarios. And so you have to look at the purity specifications, conversion rates for your technology, depending on what type of technology it is. There could be conversion rates, heat duties, rate constants, and of course the emissions potential from the technology. And so getting the useful information for the technology or the TEA is important. So development of material and energy balances need to be consistent with the baseline procedure. If you're comparing the novel technology to a baseline, you have to ensure that the design basis is important for understanding, for doing an apples to apples comparison to the baseline. And then you have to make sure that you have significant detail and sufficient detail to model the novel equipment bases, such as the design equations, scaling methodology, etc. Next slide, please. Cost estimation, of course, is important when you're looking at the technology itself. NETL uses the AACE estimate class, where you're looking at different levels of accuracy depending on the project definition. So a concept screening, a feasibility study, or a budget estimate has different percentages of the project definition, and they're based on different things. A concept screening is based on technical analogs or engineering judgment. So therefore, the accuracy of the cost estimation is a lot wider there. And then as you progress, you have more details on your technology. You can hone that cost estimate down as you progress up the TRL scale as well. So capital cost estimation, capital cost charge factors, contingencies, global economic assumptions should be considered. And I want to kind of jump back to the question that was asked during Tim Scone's presentation about the economic tax, or the carbon tax credits. Obviously, that is an important factor to consider, as it's going to change the economics of your technology that you're looking at, depending on how it's defined for your particular country, whether it's in place or it's pending, can be a difference. So the recommendation I would make is to include it as early as possible, depending on the data and the readiness of your technology. But you may want to look at doing a comparison that includes that tax and one that doesn't include that tax, so you can judge the impact of the financial assistance, and if that is needed to make your technology competitive in the society. Next slide. And so then, of course, reporting your results is important. This is the main deliverable. You've already discussed the technology analysis plan with the end users. Now you're providing them the results to make sure that you've met the objective of the study. Those include the block flow diagrams, simulation models, material and energy balances, the assumptions for the cost estimation based on what the comparison metrics are. And this is an important consideration, especially for carbon utilization. You can look at what is the allowable cost of CO2 coming in. You can look at the cost of the product generated. You can look at minimizing the energy input, so that if dependent on whether you're using renewable energy that has a very low cost, or you have a fluctuating cost of the energy input, those metrics need to be well defined and understood to make a good apples to apples comparison. So then the sensitivity studies, so you hold something constant. For example, what happens if the cost of carbon is allowed to fluctuate? How does that affect the technology itself? Can the capital be a little more expensive if you're able to pay less for the CO2, et cetera? So those types of considerations are very important. And so then obviously using the guidelines that Yusung brought up, the slide showing the templates and whatnot, that is a recommended method for reporting your results. Next slide, please. So once again, the data set that you have is very important. The confidence in the results of your techno-economic analysis will depend on the technology readiness level and the available data of the technology. Benchmark products and processes are utilized to compare products of carbon utilization technologies, and data collection is iterative to improve the quality. You may start a techno-economic assessment at a very low technology readiness level to get input on direction of where the research should go to improve the process. And then as additional data is generated, you can bring that in and hone down the confidence in the techno-economic analysis results. So NETL and GCI have conducted a wide variety of techno-economic analysis. NETL is focused primarily in the past on power generating systems, but we've also looked at carbon utilization technologies to draw comparison from. Some examples are coal and natural gas power plants, carbon capture technologies themselves. We've looked at different conversion pathways for utilization technologies, algae, mineralization, electrochemical, other biological means, and even microwave-based. Next slide, please. So I'll finalize or summarize and finish up my talk with the expected results. So once again, kind of honing down on one of the metrics. One of the most informative metrics for carbon utilization technologies is the amount of CO2 that could be utilized and the resulting break-even allowable CO2 cost for the reactant that you would pay for your process. And that should be presented for comparison in each case. However, depending on the technology, the metrics could be different metrics could be more applicable and should also be considered. Development, determination of a methodology for apples to apples test case comparison of the chosen technologies and pathways. Once again, honing down on the importance of being consistent here. And then, as Yusung mentioned, we're going to be collaborating with the technology learning curve team and the other teams to assess mineralization and CO2 to jet fuel pathways. I believe that is it for my slides. Thank you for your time, and I'm happy to be part of the discussion and answer any questions along with Yusung. Yeah, so there was a question about what I meant by carbon capture agnostic, and I believe that some of the other members already replied to that. What I meant by that is that if you're just looking at a cost of the carbon coming in, then it doesn't really matter where the carbon came from a technology perspective. Obviously, that's going to be a lot more important from a life cycle perspective. So if we're not talking about the purity of the CO2, if we're just talking about the cost, then how that CO2 arrives at the gate, the technology could be agnostic to that. That's what I meant by that. So appreciate the question on the clarification.
There's one question. The question was how consider the trade-offs in cost and emission reductions? And I think that's a really good question. So that's actually why we performed the TNLCA with the harmonized data sets and conditions. So even if we can reduce the greenhouse gas emissions significantly, if that does not economically feasible or sustainable, that does not make sense. So that's why we performed the TNLCA. And once we have the results, LCA results and the TA results, we can even calculate the GHG emission, like mitigation costs, something like that, like how much money will be required to reduce a certain amount of this like CO2 from the atmosphere. So that's the way that we can consider the trade-offs between the cost and emission reductions.
So there was a question to me, where do you find machinery costs and how do you approach scaling these? So that really depends on how novel the machinery cost is. If it's something that's pretty standard, we get quotations from vendors, which gives a very, very tight response on the cost of these. And the follow-up on the scaling approach, obviously, if you're looking at different scales of a technology that's out in the future, we do have a strategy guide for capital cost scaling, and we utilize that. I can make sure that the reference to that document is provided. It's going to be able to give you a lot better answer than what I could provide in a short time here. Thank you for the question. There's another question about, is there a GCI and or NETL web page that details the AACE estimate class used for CCUS? I don't think we have anything dedicated on the NETL page that describes that. However, I can find the reference this is pulled from. It's a pretty standard estimation class here in the US that I could provide. I don't know if GCI has something similar that they draw from.
We can certainly do the same thing, Gregory. This is Volker. I think this might also be a suggested addition to the CCUS access website, so that people can find such information there. So we'll let Grant know about this.
There's a question. Maybe I'm wrong, but I just wonder if TEA and MACC is similar. I have to admit I'm not aware of what MACC is, what that acronym is. Could you follow up and maybe I can give you a sufficient answer? So the marginal abatement cost curve, I have to admit I'm not familiar with this approach. So I'd have to get more details on that. If anybody else on the panel is able to answer that question, I don't want to, I'm going to just say I don't know right now.
So I'm not quite, I'm not 100% sure, but based on the terminology, the marginal abatement cost curve, it seems like as I just answered, in order for us to capture and utilize the CO2, and how much is CO2 be reduced based on which cost, like from the low cost to higher cost, and that the curve will be accumulated over time by having more and more CO2 be captured and utilized. But I don't know how this would be comparable with the TA. So that part is I think we may need to follow up after this call.
Okay, thank you.
If you'd like, I can help take that question. In the lifecycle analysis program, we do marginal abatement cost curve analysis, and really is a combination of the technoeconomic and the lifecycle analysis results. And so there, it's kind of, think about it as a supply curve for reduction of something. And so different investments for reduction come at a different cost perspective. So if I have 5 different options that I can make an investment in reducing a certain unit of carbon from entering the atmosphere, which is the marginal abatement cost, each one of those, like an electricity dispatch curve, has a point where it is most economically viable. Sometimes solutions are at a low cost and an easy reduction opportunity, while others, while may have a large magnitude in greenhouse gas reduction or carbon reduction, may come in at a very high cost. It may be outside the economic range of deployment. The marginal abatement cost curve helps you understand those different options. And so you would take the results of multiple TEAs for cost reduction, lay that across your environmental performance, set it the metric for CO2 reduction or carbon abatement. And you would be able to get an assessment of which ones are economically viable versus which ones may not be economically viable and require further investment to make them deployable into the commercial. So to answer the question in a short frame, the marginal abatement cost uses results for both a technoeconomic and an LCA and combines those to help inform information about reduction strategies. Great question. Thank you. Back to you, Greg and Yusing.
Well, Tim, it seems like there's actually a follow-up. There's a question that, hi, Tim, is marginal abatement cost the same as cost of CO2 avoided?
Good question. There are, depending on where you come from the lens, sometimes those definitions do vary depending on the audience. So a marginal abatement cost can be set at the metric of the CO2 avoided cost. You just need to be specific in what metric you define for that. But in general, the answer is yes. But be careful, different areas have different definitions for terminology, which is why this harmonization group is working to bring those together in a consistent manner. Thank you.
Thanks, Tim, for the assistance there.
Sung and Greg, thank you both for this wonderful third part of today's webinar. I'm very grateful also to the audience for all the questions and comments. Keep them coming, as I keep saying. The overall community will benefit from the community wisdom and questions. With that said, we have the next webinar coming up tomorrow, and I hope that many of you will join us again, same time, same location, via Zoom, with the link that you will keep receiving for up-to-date information. So thank you again for joining us. The recordings, and as teams might share their slides, will become available over the next few days. So you have a chance to review the material and continue to bring feedback to us. Thank you, everyone, and have a wonderful rest of the day.